So let's take the example where we have two materials, material A and material B. And what do we know about this? So I think, let's say both of them have the same conductivity. The only difference here is that you have different length scales for A and B. So there's LA and LB. And our job is to figure out the heat transfer. So let's draw it this way. So let's figure out the heat transfer Q dot. It's going from A to B. And let's say over here, draw this way. So over here on this side, we know this is TA. Over here on this side, we know this is TB. Okay, what we don't know is anything about what's happening right here. So this is, let's call this TAB. We don't know that temperature. So we can take this idea of thermal resistance and start applying it. So we start just like stacking it up in this sequence, and we get back like useful information. Okay, so how do we do that? So let's remember, if we have just one material, it's temperature, boundary condition. We can write it in terms of thermal resistance. So the first thing we're going to do is we're going to draw this resistance network. So in this case, let's say we're going to start on this side with our node TA. Going into TA, we have some Q dot. Then we have this thermal resistance across material A. We have TAB. Again, we don't know TAB. Now we have another thermal resistance across B. And then we have TB. All right. So again, assuming we know, I'm going to use circle stuff that we know. So assuming we know Q dot, or sorry, not Q dot. So assuming we know TA, TB, and we know that the conductivity in both of them is K. Also, we know that there's a certain area, AC. Right? So the blue stuff here is stuff that we know. So given that information, we can compute the heat transfer. So how does that work? Right? We don't know TAB, so how do we go from just what we have to being able to compute or resolve the system of equations? Well, remember, I guess maybe you remember from circuits, you can stack up these resistances. So we can say, in fact, that Q dot is equal to TA minus TB over R total, the total resistance between those two potentials. So the total resistance here, let's go up here, R total, is what? How would I write that? Let's call this RA, and let's call this RB. Any ideas how we write that? I'll give you a hint. RA plus RB, right? So we're in series, so we just add up those resistances. Okay, so we can compute RA and RB from, right, this is going to be thickness, so that's LA over KAC. This one is LB over KAC. And we have all that information. We compute our total. We can get our total heat transfer. All right? What about this TAB? So let's say it's like important for us to know what that intermediate temperature is. How do we get that? Right? Well, we just spent time figuring out what Q dot is. Right? So out of this relationship, we now have Q dot, so check. So we can take that knowledge and apply it in a new equation. Let's say Q dot is equal to TA minus TAB over RA. Right, so this heat transfer rate is the same heat transfer rate in all situations. We're just now taking this new potential, this TA minus TAB, and a resistance that we know, and using this equation, we say we solve it for TAB, and then we can compute TAB. Right, so we're solve for this. Okay, any questions on this? Okay, so thermal resistance is simple. right, conceptually, but it's a really powerful way to understand a problem. So apply it liberally, like do it all the time. If you're ever unsure about what's happening in a problem, I would say start with thermal resistance, think about it in those terms, and then see where you go from there. Okay. So let's add a little bit more subtlety to this. So we have a really simple setup where we know TA and TB. What happens if you have like different conditions? So let's, sorry, I guess red doesn't show up very well. Let me just write it this way. Q dot, TAB, TB. So now we have basically the same situation, but instead of, let's say instead of knowing TB here, right, this now becomes unknown, and we instead know T infinity, and we know that there's both convection and radiation occurring. So now let's actually draw out the resistance network for this, okay? So let's start, we're gonna go from the same place we started. So we have some heat transfer going into this node at TA. Now we again have a resistance, RA, and we have another resistance here, RB. Those are both conduction resistances. We can also introduce convection and radiation resistances. I'll go over those on a couple slides, okay? So, but for now, just take me at my word that there are resistances that we can use to represent those things. So we have a series resistance, an interface at this, the end of the domain, and then we have convection and radiation to T infinity. So how do we then draw this? Right? Anybody remember how to do parallel? Right, so you kind of go like this. So we have a resistance like this and a resistance like this. So we'll call this R convection, we'll call this R radiation, and then the potential or the difference here is T infinity. Okay, so we've developed now this thermal network, or this thermal resistance network that we can solve, right? You can represent this in the same way, compute R total and solve it. Let me just write out how it actually looks to solve. So let's say we want to compute R total, right? And that is going from TA to T infinity. So R total, let's draw it down here, is going to be equal to the series resistance of RA plus RB plus, I guess, this combined resistance, right? The our convection and our radiation are both together in series with the other stuff. So we have to come up with our combined radiation and convection resistance for that part. So anybody remember how to write parallel resistances? So R parallel is 1 over R1 plus 1 over R2 plus let's say do dot, 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 plus 1 over Rn to the minus 1 power. Okay, so you could have like, we have 2 in this case, but you could have any number in parallel. This is how you convert it to this parallel resistance. So for us, up here, it's going to look like this. 1 over R radiation plus 1 over R convection to the minus 1 power. Don't forget that minus 1 power. People do that all the time. It's really saying it's 1 over that whole quantity, right? Don't forget that. So that's our R total. We know TA, we know T infinity. We can compute heat transfer for this problem. Okay. Questions on that? All right. It seems pretty straightforward, at least when I'm talking about it. I guess when it comes to applying it, then it gets trickier, right?